Alright, welcome back, guys. We're going to go ahead and finish up this 2.5 measures of position. So we had just got finished making a box and whisker plot, okay, using the 5-number summary. And we also talked a little bit about how just by looking at this box and whisker plot we can kind of tell how the data is sort of distributed. Okay. Alright, so now we're going to talk about some other fractiles. Now, their deciles are used, guys, but not all that common. So what a decile does is essentially it splits the data set up into tenths. Okay, so it'd be like the tenth or the first decile, the second decile, the third decile. Those would correspond to the 10th percentile, the 20th percentile, the 30th percentile, etc. But we're mainly just going to focus on percentiles. Okay, and I've got an example right here of some SAT scores. And anytime you see a graph, this is an ogive, it's going to be increasing. Okay. And so if you're looking at this, you can see that for each score, or each point here, there's a corresponding percentile. So this particular example, it says, what score corresponds to the 80th percentile? Well, the percentiles here are graphed on the vertical axis. Now, I know they go in increments of 10, so because they do go in tens, you could also, it'd be easy to find the decile, but anyway, the 80th percentile is right here, and if we look over, we find this point, and the actual score that's associated with this point, or the 80th percentile, in other words, appears to be about 1250, okay, 1250, which is actually a pretty good score for the SAT. That's why anybody that scores at 1250 is in the 80th percentile. Alright, so to find the percentile of a specific data entry, you use this formula right here. So if you're trying to find, in that previous example, we were trying to find the 80th percentile, we would just figure out, if we were trying to figure out what percentile corresponded to a score of 1250 on the SAT, we would calculate all the data entries that are less than 1250 divided by the total number of data entries and multiply that by 100, and that would give us the percentile. Okay, and so that's what we're going to do in this next one. So a percentile, guys, is really just a percentage of data that's at or below that specific value in the distribution. Okay. All right, so example 5 here. The data here is weekly salaries in dollars for a sample of registered nurses. Okay, so you can see these are ranging anywhere from 619 all the way to 1,194. So what we want to do is see what a salary of $1,083 per week for this specific week represents as a percentile. What percentile would 1083 be? And so to do this, we're going to count the number of data values that are strictly below 1083. Okay. So you could even mark these off if you wanted. This one's below, this one, and this one. And so it appears as though there are 5 that are below. Okay, I'm going to say 5 entries less than $1,083. And we're going to divide this by the total number of data entries. Okay, and the total is 8. So 5 divided by 8 I believe that's 0.625. And if we multiply that by 100, we are going to get 62.5%. So you could say the 62nd or the 63rd percentile. So in the context of this problem, that just means that roughly 62% of nurses are going to be making at or below $1,083. Okay. All right, example 6. Okay, and all of those standardized tests that you took when you were in school, the results were always, or at least when I was in school, they were always percentiles. They would give you your raw score, but that didn't mean anything. Okay, you didn't really know how well you did until you could look at it as a percentile with relation to how everyone else scored. The raw score itself was meaningless. Alright, so this says a student's grade of 75 represents the 65th percentile of grades. So that means that 65% of all other grades are going to be at or below 75. So the question is, what percent of students scored higher than 75? Well, this one's not too difficult. It's just going to be 100% minus the percentage that scored less than or equal to 75, okay, which is 65%, because 75 corresponds to the 65th percentile, so that's going to leave us 35%. So you could say 65% of the grades are going to be at or below 75, and then 35% are going to be above. All right. And then here's a little graphic you can read if you want. It just says, make sure you understand what a percentile is. We're used to using percentages, so you say, oh, okay, if I got a 90% on the test, then I did pretty well. And in a sense, that is a percentile because it means that you got 90 out of 100 of the points, or not 90% of the test was correct. Okay. Here's another example. It says the weight of a 6-month-old infant is at the 78th percentile. So what this means is that the weight of this particular infant is greater than or equal to 78% of all the other weights. Okay. And then down here it says it does not mean that the infant weighs 78% of some kind of ideal weight. Okay. All right, so remember, these percentages, they're just about position. Where's the position of this particular data value in relation to the entire distribution? What percentage of the distribution is at or below that particular data value? All right, and then the last thing that we're going to talk about in this section is the standard score. This is also known as the Z-score, guys. I'll be talking about this a lot throughout this course, by the way. Okay. So the Z-score, the standard score, so every single distribution is going to have a mean. And every single distribution is going to have a standard deviation. So the mean is the measure of centrality, and if we're talking about a bell-shaped distribution, then the mean is going to be in the middle. And then the standard deviation is a way to quantify how spread out the data is, how much variation there is in the data. Okay. Well, a Z-score is basically a value that's associated with a specific data value in terms of standard deviations. So it essentially tells you how far away from the mean is this particular data value in numbers of standard deviations. So if I say, we took this test and, we don't care how many points there were, but the person that scored, that obtained 60 points, the z-score associated with that is 2. So that means that that particular score is 2 standard deviations above whatever the mean was. Or if that score had a z-score of -2, that means that particular score was 2 standard deviations below the average, okay, which wouldn't be good, grade-wise anyway. All right, and this is how it's defined mathematically. Okay, so the z-score is equal to the specific data value minus the mean. So this is where this tells you how far away from the mean the particular data value is, and then you divide it by the standard deviation. Okay, now we're assuming this is a population, so that's why we're using mu and sigma here, and x is the actual data value. And so what this will tell you, or whatever this number is the number of standard deviations away from the mean that particular data value is. So let me use that IQ example again. I think I told you that if the average IQ is 100 and the standard deviation for that particular distribution is 15, then somebody with an IQ of 130 would be 2 standard deviations above the mean, because 15 and 15 is 30. So the z-score associated with a raw score of 130 would be 2 standard deviations. Okay. All right, now let's look at some of these bullets here. A negative z-score just means that that particular data value is below the mean. A positive z-score means that that data value is above the mean, or greater than the mean. And then a z-score that's 0 means that x value is actually equal to the mean. Okay? So the z-score is telling you how far away is that data value from the mean in terms of standard deviations. Or in other words, how many standard deviations would it take for us to go from the mean to that particular data value? All right, so let's keep going. So usually z-scores fall between, most z-scores will fall between -2 and 2. Because if you remember from the empirical rule, and I've got it up here in the last set of notes, within 2 standard deviations, okay, so from 2 below to 2 above, we have 95% of the distribution, or the data. So that's why it says right here that usually the z-scores are going to fall between -2 and 2, because that's where 95% of the data is going to be. And then the number of z-scores outside of this range are only going to occur about 5% of the time, because if 95% of the data is between 2 standard deviations, then the other 5% will be on the other side, or will be in the tails. Okay, and then it's very similar. There will hardly be any z-scores beyond -3 or +3. In fact, if you look here back at the empirical rule, from -3 to +3 standard deviations, you have almost 100% of the data set. Okay, so a z-score outside of -3 and 3 would be considered very unusual, occurring less than 0.3% of the time. Okay, and so here's your little graphic. We say anything that's within 2 standard deviations from the mean is usual. Anything beyond 2 standard deviations but less than 3 standard deviations is unusual. And then anything beyond 3 standard deviations is considered very unusual, or quite rare. Okay. All right. So let's look at these last 2 examples. So example 7 here, it says, suppose a student takes a statistics test and a biology test. He or she scores a 60 on the statistics test and a 20 on the biology test. So those are the actual raw scores. The mean for the entire statistics class is 63 with a standard deviation of 7. And then the mean for the biology test is 23 with a standard deviation of 3.9. And so what we want to do here is transform the student's raw test scores into z-scores and then determine on which test the student had a better score. Okay. All right, so let's do the statistics test first. All right, so if you remember this formula, the z-score will be equal to the actual data value minus the mean divided by the standard deviation. Okay. All right, so for the statistics test, he scores a 60. That's going to be 60 minus the mean on the statistics test was 63, divided by the standard deviation, which is 7. Okay? So this would end up giving us negative 3 divided by 7. And if we use the calculator, we're going to get this would be negative 0.4286. Okay. So that's the z-score for the statistics test. It's negative because 60 is below 63, right? He scored below the mean. But it's only about a half of a standard deviation below the mean, because 3 is about half of 7. All right, now what about for the biology test? Okay, well, very similarly, it's going to be the actual score on the biology test, which is a 20. Okay, so it's 20 minus the mean on the biology test is 23, divided by the standard deviation, which is 3.9. Okay, so this would give us negative 3 over 3.9, and this is actually going to be further from the mean, but in the negative direction. Negative 3 divided by 3.9. So if I carry this out to 4 decimal places, it'll be negative 0.7692. Okay. All right, so we can compare these now. Whenever you convert a raw score into a z-score or a standard score, guys, you say that you've standardized that score. Okay, and so each of these scores has been standardized, so only now can we actually determine in which class he did better on this particular exam. It's very similar to that coefficient of variation, right? You may know the standard deviation of a data set, but until you actually compare it with the mean, you don't really know how large it is. All right, well, you can see that this value is actually a little bit larger than the other value, okay? On both tests, he scored below the average, which isn't great. But here he was closer to having scored average. So he scored better on the statistics test. Oops. Okay. Also, I will mention something that I probably mentioned this before. When people talk about grading on the curve, they're talking about using z-scores to assign grades. Okay, so if you look at this graphic that I have up here, Anything within one standard deviation above the mean or below the mean is rendered a C. And then anything within 2 standard deviations, but outside of 1 standard deviation from the mean, it would be given a grade of B. And then anything beyond 2 standard deviations, well, actually, yeah, I'm getting this wrong, because over here on this other, well, let me show you like this. So anything in this middle would be given a C. But anything between 1 and 2 standard deviations above the mean is given an A, and then anything beyond 2 above the mean is given a B. Now on the other side, anything from 1 standard deviation to 2 standard deviations below the mean would be assigned a D, and then anything below 2 standard deviations from the mean would be assigned an F. That's what it means to grade on the curve. Okay, and what this means is that you're competing not to make a perfect, rather you are competing with your classmates. You're trying to see how far above average you can score. That's what determines your grade. But anyway, I'm going to erase this for now because I don't want you to get confused. Alright, so let's look at this last one. Okay, so this one, it says the lifespan of a series, of a species of fruit fly, or the lifespans of a species of fruit fly have a bell-shaped distribution. Okay, so we've got to, it's got to be have this distribution before we can really talk about much of this stuff. With a mean of 33 days and a standard deviation of 4 days. And so the lifespans of 3 randomly selected fruit flies are given. 34 days, 30 days, and 42 days. So we want to find the associated z-scores to each of those actual lifespans, and then determine whether any of these lifespans are unusual. So again, we would deem them unusual if they are beyond 2 standard deviations. Okay, really between 2 and 3. But anyway, let's go ahead and do these. Okay, so for the 34 days, remember again, to find the z-score, it's the actual data value minus the mean divided by the standard deviation. So 34 minus the mean is 33 days. Okay, this is given to us. And the standard deviation is 4, so this is going to end up being 1/4, which is 0.25. So a z-score of 0.25, so this is a little bit above average. And then for the lifespan of 30 days, it would be 30 minus the mean divided by the standard deviation, and this would be negative 3/4, which is a negative 0.75. So this particular fruit fly didn't quite make it to the average lifespan. And then finally, this next one's going to be the ancient fruit fly. 42 days minus the mean, which is 33, divided by the standard deviation. This is going to be 9 divided by 4, and that, guys, is actually 2.25. So this particular fruit fly that lived 42 days, because that fruit fly lived beyond 2 standard deviations, we're going to say this is unusual for a fruit fly. Now, in order for us to say this, we are assuming that the distribution of lifespans for fruit flies is bell-shaped. If that weren't the case, we could not make these assumptions, or assertions rather. Okay. Oops. All right, part B. So the lifespans of 3 randomly selected fruit flies, again, are 29, 41, and 25 days respectively. So using the empirical rule, find the percentile that corresponds to each lifespan. All right. Well, the first thing we need to do, before we can use the empirical rule, we need to know the actual z-score. We need to know how far away from the mean in standard deviations these actual lifespans are. So we're going to do the same thing. Well, 29 minus the mean divided by the standard deviation. This will be negative 4 over 4, which is negative 1. Okay. And then the next one, 41 minus 33 divided by 4. It's going to be 8 over 4, which is 2. So 41 days is 2 standard deviations above the mean. And then finally 25, this one, this is the young, reckless fruit fly right here. 25 minus 33 divided by 4 is negative 8 over 4, which is negative 2. Yeah, so this fruit fly didn't make it too long. All right, now before we can start trying to figure out, okay, well, you know, what percentage of fruit flies lived fewer than 29 days or lived less than 1 standard deviation below the mean, I like to draw a picture, okay? And I think this will help you guys out as well. So let's go ahead and just kind of draw my bell curve here. And so here's the mean, and right here is negative 1. Okay, so this is what we're talking about right here. All right, so the percentile that corresponds to negative 1, or also that corresponds to this particular 29-day lifespan, is going to be essentially the area that's to the left. Well, I need to get the marker. Okay, so it's all of this area right here, right? Because isn't that what a percentile is? It's the percentage of the distribution that's at or below that particular value. All right, well, to figure this out, guys, remember, we've got to think back to the empirical rule. The empirical rule said that from negative 1 to positive 1, there was 68% of the data, right? I'll show you. See this in blue right here? Within 1 standard deviation, we have about 68% of the data. So if I have 68% within 1 standard deviation, then that must mean that I have 100 minus 68, which is 32%, outside of this. So that would be 32% in both of these tails. Well, both of these tails would comprise 32%. So that means in one tail individually there would just be 16%, right? Since there's 2 tails, I divide by 2, so there's 16% here, and there's also 16% right here. All right. Well, by doing this, I think we figured this out. If the area right here in this leftmost tail is 16%, then that is the actual percentile. 29 days is the 16th percentile. Okay. So guys, on these, you may need to draw your little picture and try to figure out how much of the distribution do I have in each little piece. Okay. And then we're going to do the same thing for this next one. All right, now this one, okay, so again, the mean is right here in the center. This one has 2 standard deviations. It's way over here. Okay, so we're trying to find the percentage of data that is to the left. So all of this right here, okay? There's several, all right, let me draw a little bar right here. So there's several ways that you can think about this. I'm going to take the approach that I used previously. The empirical rule tells us that within 2 standard deviations of the mean, we have 95% of our data. So that means from right here, -2 to +2, we have 95% of the data. Okay? Which means that there must be another 5% in the 2 tails. And if we divide that by 2, that means we're going to have 2.5% in the right tail and another 2.5% in this left tail. Okay? So then how much do we have together to the left of 2? Because that's the z-score for 41 days. Well, it's this whole region here in the center, which is 95, plus this extra 2.5%. So we'll say 95 plus 2.5 is 97.5%. So 41 days is the 97.5th percentile. So if you're a fruit fly and you're living to 41 days, you are living as long or longer as 97.5% of all other fruit flies. All right, so what about this last one? And guys, the more you work with these, the easier this will become. So see, you know, when they say 2 standard deviations, think about 95%, which means there's going to be 5% in the tails, which means each tail will only have 2.5%. Okay, and that'll actually help us with this next one. So see, the next one, 25 days, corresponds to a z-score of -2. So the mean's still in the middle, but -2 is way over here. Now, I could approach this the same way and say from -2 to +2, there's 95%, but I'm really just looking for the percentage of data that's to the left of -2. Well, we just figured that out in this previous problem, didn't we? We just determined that below 2 standard deviations, there's only 2.5% of the distribution. Okay, so then we can say that 25 days is the 2.5th, no, 2 point, well, yeah, I guess it's the 2.5 percentile. Okay, so this means that if you're only living 25 days, then you're only living more than 2.5% of all other fruit flies, which means that other 97.5% of fruit flies is outliving you. So anyway, guys, you'll have to do problems like this again in this course. So like I said, go ahead and get comfortable with drawing these distributions out. Try to memorize, you know, how much of the distribution is within each of those standard deviations. And I think that'll make this a lot easier. And the more you do this too, you'll be able to remember how much is going to be in the tails as well. All right, but anyway, that'll conclude this last section of Chapter 2, guys. So that's it for Chapter 2. So remember, all of Chapter 2 is on what we refer to as descriptive statistics. So when we have a data set, if we have a sample, okay, we find these statistics and they describe the data set. And then from those statistics, we can make inferences. All right, so the next thing that we will cover will be probability in Chapter 3. Okay, so I will see you there.